Today I'm going to be going over your analysis for your project in exploring average minimum temperature in Salt Lake City. And on the left here, I have the items that we need to cover for your analysis. And on the right here, I have RStudio, which is a statistical analysis software. And I'm going to go over the commands to get our analysis in RStudio, but instead of requiring you to know RStudio, I'm going to provide its output for you. Okay, and so I will paste this into this document here and upload it for you to use. Now, the first question here asks us to provide a scatter plot of average minimum temperature in year with the regression line in one plot. So this first set of commands right here, that's just loading the data, okay? And once I run this, I can look at my data, just a little bit of it, by doing this head command. That gives me a little bit of the data. So here I have the year, I have the T-min, I have T-max. I want to plot T-min, average minimum temperature, on the y-axis and year on the x-axis. Okay. Now, as you can see, the smallest year is 1949. If I want to know the largest value of year, I can just ask for it via the max function. So I can see that the largest year is 2017, the smallest year is 1949, and so my data corresponds from 1949 to 2017. Okay. Now I'm going to go ahead and provide the scatter plot, and here's the plot of the data. On this bottom right hand side, this little console on the bottom right, I plotted my average minimum temperature on the y-axis, and on the year I have corresponds to the x-axis. Now I'm going to do this command called AB line that will plot the regression line against the data. So that is the regression line plotted against the data in one graph. I'm going to go ahead and export this, and I'll copy and paste it into this document for you so you can have access to it. Let's do 400 by 500, and let's take a little sneak peek of a preview. Maybe a little bit taller there. Sure. Okay. So there's our graph for us. We've done it. Now, these next question right here, it's asking us how much does the temperature change every 10 years according to the model. Well, according to what model? Well, according to a linear regression model. So to answer this question, you're going to need some linear regression model. And so let's run the linear regression model. You see I ran this command here. It did a linear regression. You didn't see any output because I didn't ask it for the output yet. Okay. So I'm going to do the summary command of this linear. Okay. That's what I call the linear model. I named it linear. Okay. So if I ask for the summary, this is the output. Okay. And what you really need is just this little bit here. I'm going to provide you all of this. We'll use one other thing here. This is our linear regression model. Okay. Right here. It didn't copy and paste that well. So let me see if there's something I can do to help with that. Numbers want to come up. That's not what I want. But let me go ahead and format this a little bit better for us. So there we go, there's our estimate. The next thing we have is a standard error. Then we have a t-value, which we haven't talked about yet. And we also have something called a p-value. This p-value is important. Okay. Okay. So those are the significance codes for the p-value. But we also don't need that. That's okay. Okay. So this is the basis of our output right here. And based on this linear regression model, we can write down the equation. And if I were to ask you what the equation is, what you'd look at is you'd look at this estimate. Okay. This value right here, and I'll color that or highlight it once I have a chance here. So there we go. And there we go. The equation says y, which represents average minimum temperature, is a function of y equals mx plus b. Here, x represents year. So m is given by this coefficient right here, this 0.0836. And we multiply this by year, and we subtract minus 124. I guess I'll put a times down there just to try and make this a little better. And using this equation that came from this output, okay, you can answer this question. I'm not going to answer it for you, but you can answer this question by how much does the temperature change every 10 years according to this model. And all you have to do is you have to inspect this output, this equation, and think about changing the year and by how much is it asking you. Okay. Now, this part B, this part right here, it asks us to state our regression model in the form of an equation. Well, we did that right here. So why don't I copy and paste that and put that right here. Okay, that is our equation. Now you can format it in a different way if you like. And you know, I didn't use that many decimal places. You can use more or less if you want. I think it's fine the way it is. But you can use this question to answer, hey, what would a slope of 0 imply about this relationship between average minimum temperature and year? So it's asking, hey, this is your slope m. What if m was 0? So this part right here, this is asking you, what would happen if m was 0? Okay. Now, here's another question we have here. It asks us, what is the correlation coefficient between average minimum temperature and time? What is the meaning of this numerical value? And what does the square of this value say at the model? Well, it just so turns out a measure of the square of the value can be taken there. And let's use a different color. I guess I'll use that color. Okay. multiple r squared, you can use either of these two values, is given here. That's the square of the correlation coefficient. Okay. Now, you have two different numbers you could use. You could use the multiple r squared, which is the traditional correlation, coefficient squared, or this adjusted one is one that's modified. And it's talked about in your textbook, but it's not required material. Okay, so I'll let you decide which one of these you want to use, and I won't highlight that part. Okay, so if you have the square of the correlation coefficient, I think that we can determine what is the correlation coefficient. Well, I mean, it says this is the square of it, so if I want just the correlation coefficient, I think I just need to take the square root of that number. So let's insert an equation here, and it will be this. Well, we'll do the 0.624, but we could have done the 0.6183. That's the more conservative estimate. Okay. And you need to calculate what this value is. I don't just want the square root. I want to know what is the actual value of the square root. But I'll leave that for you to do. Okay. Now, a comment here is I told you what these values are, and I'm going to ask you to explain the meaning of this number in your paper, because there is an interpretation for this, and it is covered in this course. Okay. Likewise here, I want you to explain the meaning of this number in your paper. Okay, and that's within the context of data analysis. Okay, because it has meaning. We've gone over the meaning of a correlation coefficient, and if you're not sure what it is, please look it up in your notes or in the textbook. Okay. Okay. So, like here, comment on the when the regression model applies. Hey, we got this equation right here. It says average minimum temperature is this. This doesn't always make sense to say average minimum temperature is 0.0836 times year minus 124, because this predicts a temperature of minus 124 degrees Fahrenheit when the year was 0. Okay, and you have to tell me if that makes sense or not, if you think that's feasible. But if we look at the scatter plot of this data, it seems to be a reasonable fit for some values of the years. I want to know, like, do you think that it only applies between 1970 and 1980, this regression line? Does it apply to 2010? Does it apply beyond 2010? Like, would you be, excuse me, 2010. And our last observation here, when we computed it, well, I'd have to look at it. The maximum observation we had was, that was the minimum. The maximum was 2017. Does it apply for 2017? Would it apply for 2020? Would it apply for 2030? How confident would you be in making inferences or predictions to model the data beyond maybe the year 2017 or before 1950? Okay. Okay. So those are things that I want you to address in your paper. Now we've come to this assumptions section. The assumptions of regression are normality, and we have ways of assessing that. That might be via a box plot or a histogram, constant variance, and independence. Okay. And I want to correct the grammar there, so my apologies. So to assess normality, it's asking us to make a histogram of the residuals. And to assess equal variance, we're going to plot the residuals versus the fitted. Okay. So I'm going to go ahead and do this part of this, and then you'll have to comment on what you think the histogram and the plot of residuals versus fitted means. Okay. So let's do the histogram of residuals. Okay. And so there's this command in R called hist, and I'm going to do it for the residuals so I can nicely access them this way. And let me put a legend here. Normality of the error terms. Okay. And let me put something on the x-axis. Let's just format this so it's nice. So x lab equals, let's just call it x, or, okay. It wants a comma. Okay, there we go. So you'll have to answer if you think this represents a normal distribution, what it tells us about our linear regression, and so on. So really, I want to put this in your mind that when you're writing your paper, it's not just a cut and paste job of this analysis that I'm pasting in here. I'm expecting you to interpret these results. Okay. So let's copy this to the clipboard. Let's make that a little bit wider, and let's take a look at it. Sure. Okay. Now it asks for the residual versus fitted values. Okay. And if I want to access this, I'm going to ask it to plot the linear model. And when it does that, it gives me a series of diagnostic plots. I only want the first one. This is the residual versus the fitted values. And I often want to tell people that, hey, sometimes this red line can be deceiving. So please ignore this red line. And the question is the spread to assess equal variance, is the spread of these points roughly constant as the value of the fitted value increases? So as x increases, is the spread from top to bottom of these points roughly equal? And let me copy that to the clipboard for you. Okay. So is this reasonable? Okay. And keep in mind that that red line, it can sometimes be there not because there's actually a curvature there, but because of random error, randomness in your data. Okay, so that's why that red line can be deceiving. Okay, then the last assumption is, do you think the data is independent? And I'm just going to give you some verbal background here with regards to temperature data. The best way I can predict tomorrow's temperature is with today's temperature. We expect them to be relatively similar. So that suggests the data is dependent. But what we do something to make the data less dependent, which is we calculate the average minimum temperature. So we take the minimum, and one thing that people do, when you're looking at minimums to make them less correlated, less dependent, is they take the average of them. So 1 year's worth of data, we're taking the average of all of that. So for this, I would say argue it is weakly dependent, because naturally it's dependent, but we're doing something to our data. We're taking the average of a whole year to try and make it less dependent. And if we think about, why an average does that, well, every year could be a little bit influenced by the previous ones, but we're just taking the average, so it's not as correlated as it would be. Okay, so that was average minimum temperature. Let's move on to maximum temperature. So this is a comment in R. And, basically I need to do all of this again. I need to reproduce a linear model, I need to reproduce a scatter plot, etc. Okay, so I'm going to rename these, and I'm going to do some things differently. So because this is for maximum temperature, I'm going to name this max, and this is not going to be Tmin, it's going to be Tmax. Okay, this is going to be Tmax again. Then I want for the maximum temperature, and for the maximum temperature, and linear dot max here, and linear dot max here. Okay. Now I'm going to provide less commentary on these problems because we've already discussed the analogous situation for minimum temperatures, and I expect you to be able to adapt and explain the output. More than anything, I want you to explain the output in your write-up. Okay. So let's run this. So here's the data, here's the regression line. Okay. I'm going to ask you if this looks very linear or not. You're going to have to decide. Let's copy this to the clipboard, copy plot. So here's your output. Let's center that. Okay. And so there we go. How much does the temperature change every 10 years according to the model? Well, we're going to need the output. Okay. I think that this is best not centered. So yeah, let me do that. And let's now get the summary of the output. So I'm going to ask for that. And here's our output. And we'll want our multiple r squared. And I'll copy and paste that here for us. Now we're going to want to have this formatted a little bit nicer. So let me do that. And then we have a t-value. And then here's our p-value. Okay. So just like last time, this estimate right here was really useful. That told us our intercept. This is our slope. Okay. We have our multiple r squared again. So I'm going to trust you to be able to interpret that. Now this p-value means that it's a test of hypotheses. And what this p-value is testing, it's testing the hypotheses and asking you if it's possible that this slope of 0.02 could be 0. After all, it's pretty small. Okay, 0.02, that's not super far from 0. Is it possible that this slope is 0? Well, this p-value is testing the null hypothesis that it's 0. Because this p-value is less than, 5%, we would reject that this slope could be 0 at the 5% level of significance, even at the 2% level of significance, because we computed the p-value. Now if we go back up, I didn't emphasize the p-value, but it's something that's important. P-value right here is 7 times 10 to the negative 16th. It's not possible that what that's telling us basically is that it's not possible this slope is 0 because of the p-value that's given us right here. Okay, and this p-value is 7 times 10 to the negative 16th. Extremely, extremely unlikely that the null hypothesis that the slope is 0 is true. Okay, and the meaning of a slope 0, well, I'm asking you to explain that in this question. What would a slope of 0 imply? So what would that null hypothesis imply? Okay, so we got some more output here. Based on this output, you can write down the equation for average maximum temperature with year. Okay, and you can answer how much does the maximum temperature change every 10 years according to the model. Okay, so you can answer this based on the output. Okay, so I'll say use the output provided. Okay, what is the correlation coefficient? And what is the meaning of this numerical value? What is the square? Well, again, use the output because the square is provided here. You can use either multiple r squared or adjusted r squared. Okay. Okay, so that pretty much answers our two linear model questions, and from here we're going to go on to comparing average minimum temperature pre and post 1980. So the first thing is to divide your data set into two, compare the histograms and the box plot for the average minimum temperature for pre versus post, report the median, the variance for pre versus post. Okay, well, this is a little bit more tricky. There are several ways to divide your data set, no matter what statistical software you're doing. I do that here with an if-else command. It's a logical command. Okay, and it says if the year is less than 1980, assign the label pre for pre-1980. And maybe since pre-1980 is technically before 1980, why don't I take that away? If the year is less than 1980, I'll assign it the word, the prefix pre or category pre. And if it's 1980 or after, it gets the words or category of post. I'll run this pre-post command, and here it is. It labeled a bunch of data as pre and a bunch as post, starting here. Okay. I could also do it this way. This is another way I could have divided the data set like this, but I actually prefer this first method. So I'm going to comment this out because I like the method that was done with the pre-post and the if-else command. Now it's asking me this. Oh, actually, I think I might need that a little bit later. Okay. It's asking me to compare the histogram and the box plot. So I'm going to do this histogram, and this is for average minimum temperature, so I'm going to do Tmin by pre-post. And let's see if this works. Okay, X must be numeric. Okay, it didn't like it. Okay, I actually need that pre-post that I had down there. But I can do the box plot. Box plot Tmin by pre-post. Okay, and here we go. Here's our box plot. Hey, look, post 1980, it has a box plot that's much higher up than the pre. I want you to tell me what that's saying. And it has quite a few observations that are outliers above, whereas the pre has an outlier that's below. That's kind of weird. Maybe you can tell me what this box plot means. Okay, let me export this and copy it to the clipboard so that you can use it and comment on it. Okay, so it asks for the box plot. Great. How about the histogram? Well, for the histogram, I'm going to actually need this, so I lied. I'm sorry. So for pre and post, why is it complaining about SL? Oh, because I named it data. I'm sorry. Data. Yeah, okay. Okay. And I'm going to do a couple of commands in R to make the graph make the graph side by side. mfrow equals C 1 2. Okay, and then so this sets my graphics window to display it side by side. I'm gonna need to reset it to display one at a time. And so I'm going to do this histogram of this pre. Okay, and I'll put main is a histogram for pre 1980. Okay, and the X label is going to be year. Oh, okay, so pre has a lot of data in it. So pre just made my data be the year. I cut the data set, not necessarily in half, but I divided it as a data set before 1980. I need to do pre, but I need to graph the Tmin. Okay, so that's pre 1980. Okay, let me do the same thing, but I need to change the label, and I need to change this to post. So that's post 1980. Okay, well let's now graph these, and then let me export these. And these don't look as great plots because they're way too small. I need a big width, maybe like 600 by 500. Okay, and that looks a lot better. So let's copy this plot so I can give it to you. And here's the plots side by side. Okay. And now it asks me to report the median, variance, and average for pre versus post. So let me do that for you. And I'm going to insert a table, pre versus post, median, average, variance. I think I'll need that many tables. So this will be pre 1980, and this will be post 1980. And I actually needed one more column. So I need a column to the left. And this is going to be the statistic. So I need the average, right? I need the median, and I need the variance. Okay. And what I want from you is to tell me what you think, you know, what is this box plot telling me? That's a visual display of data. What are these numerical statistics trying to tell me? And what are these histograms telling me? And I want it to be within reason and in your own words. Okay. So let's calculate this. So I need to do it for the pre. Let's do it for the pre first. And I need the mean of pre T-min. Okay, so that's 39.28. There's my average. Okay. Okay. Well, I need to calculate two more statistics. I need the median. That's very close to the mean, and maybe that's an indicator about if the data is normally distributed, something's true about the average and the median value. Are they close enough? What do you think? Okay. Okay, what about variance? You know, sometimes a better measure of, so I guess I'll give you some extra information because, you know, if you're interested in interpreting, standard deviation has the right units. It has units of Fahrenheit, whereas variance will be Fahrenheit squared. So, you know, they're the same. You just have to take the square root of one, but, you know, why not give you a little extra information? So this is 1.8 degrees, okay, whereas the standard deviation, wrong thing here, it's going to be 1.34 degrees. So that's how much things varied pre-1980. That was the average, that was the median. Let's try post. So here we go. Here's post. Here's post. Here's post. And here's post. Well, okay. The average was 42.35. Okay. The median is 42.08. The variance is 2.47. Okay. And the standard deviation is 1.57. Okay. So notice, the numbers have changed pre versus post. Okay. So these are all summary statistics here. Okay. Okay. So I provide you with all of the data here, and what I'm really looking for is for you to interpret these results. Okay. Okay. So notice, the average value, it's gone up from 39.2 to 42.3. You know, someone who studies statistics would say, hey, is that just random chance that it went up by that many degrees? Like, is that a bad sample? Is that due to random chance? Well, we have a tool to determine if these two, if this change is due to random chance, okay? Or if there actually is a difference. And that's a t-test. And there's a certain hypothesis, okay? And one thing that I want you to do is I want you to not state in layman's terms what the null and alternative hypothesis is. Okay. Okay, so if I want to know, has this changed, you should do a t-test. And let's do that. So I'm going to do a t.test, and I'm going to do, I created labels for my data called pre-post. So it's going to be t-min, and I'm going to compare pre versus post data. Okay, and here it is. This is my data that I get. Okay, so this is the p-value that I get for a certain null and alternative hypothesis that assesses whether the temperature has actually changed. So that's very important. I'd also like you to comment on the 95% confidence interval. That provides a confidence interval for how much we think, according to a 95% level of significance, that the temperature has increased, and by how much. So the lower end of the increase would be 2.4. The higher end is it could be as much as 3.79. Okay. Then it provides you the mean in each group. We already calculated that. Okay. So those are two really important things. Again, I would say this. You need to interpret not the graphs, but the output. So I'll just say the output. Okay. And by the way, you're welcome to do the, if you want to do the analysis for yourself, you're welcome to. You can use R, you can use Excel, you can use Python. Okay. Now, construct a 95% confidence interval for the difference in average minimum temperature. Well, that's done right here. So I'll just copy this and say you need to interpret it. Okay. And that is your data analysis that is required for this Salt Lake City temperature project. I provided you with the output, the graphs, but I haven't answered all the questions for you. Like, I haven't told you what things mean. I haven't answered every single question that is asked for here, and I will be grading you on those questions, and especially looking for the interpretation since I provided the output. Okay. Thank you for joining me, and I will look forward to reading your papers.